once they're cleaved off, they're notoriously aggregating. So they form this Abeta fibro or plaques that are found in Alzheimer's patients' brains, except there's gunk in those brains. And it's Abeta fibrils. For these reasons, people have believed that for a long time, the Abeta fibrils are the toxic species. That's what's causing the Alzheimer's disease, because they may like block the ion channel and stuff. But it turns out that the intermediate, the Abeta oligomers, are actually the neurotoxic species, which causes the Alzheimer's in the end. So as I alluded before, Abeta oligomers in the equilibrium between monomers and fibrils, fibrils being most stable species product. And we do not know much about the oligomers. One thing that we do know is they're very difficult to study. One thing we do know about the Abeta oligomers is that Abeta monomer has to adopt this beta hairpin conformation to form these Abeta oligomers. And Abeta oligomers are known to be composed of this beta hairpin or Abeta monomer. So to approach this difficult problem, the Noik lab has developed this chemical model system where, for example, this one macrocycle is templates the beta hairpin part of this Abeta sequence here. So it's L17, L17 to D23, A32, A36. Here with some interesting this model system that templates the beta hairpin. And found these chemical model systems are a lot easier to handle and a lot more stable, so that we were able to obtain this Abeta X-ray crystallographic structures and study them by NMR techniques, for example. So my first 2 years, I took this same approach here and made this peptide, synthesized this peptide that derived from trans-arretin, another amyloidogenic protein, and I was able to get this interesting flat structure here, which assembles into this. Each one of these is the macrocycle, and they form this long elongated square channel. As you can see, it's this top view where this is one of these, and their elongated view of the structure. I'm not going to focus on this project today, but and furthermore, this in 2016, Dr. Kreuzer has incorporated the beta turn region or the beta hairpin, so encompassing this whole part of this Abeta, which is about half of Abeta, and was able to get a similar trimeric assembly structure, which was a really interesting insight that we were able to learn from this model system. What I wanted to do is to study the whole peptide, so not just the half of peptide, but whole thing. So because that's the whole peptide is actually the peptogenic species, right? So I hypothesized that if I stabilize beta hairpin with sampling staple, sample a beta hairpin with a chemical bond, like covalent bond, I will maybe be able to block this pathway between Abeta monomer to the fibril and Abeta oligomers and fibrils, and be able to lock it in to stabilize the Abeta oligomers this way. So this is one of the few peptides that I was able to express in study. So this is one of the examples where I mutated a V24 and G29 into 2 cysteines, which has diol groups, which I was able to oxidize those diols to make disulfide links in the mildly oxidative condition, and form this disulfide linkage and stabilize the beta hairpin region. So before I to test this hypothesis, I needed to ways to synthesize a lot of different mutants quickly and with high purity, right? So I had a few options in the beginning. So first,